the long name is Master Autoencoders are scalable vision lens, and these are the authors, and they are all from Facebook here, and this is a CVPR 2022 paper, although it was like published in December 2021. And just to get a start, so we know what autoencoders are. It's something like this. There's an encoder and there's a decoder, and what we simply do is we give input and try to maybe reconstruct it according to the task. And so then what is master autoencoders? So again, there will be an encoder, autoencoder, and so master autoencoder means we can think of this. The input is sharing mask, but that's not what happens. So we'll go into depth and understand what that is. So generally, like looking at representation learning, we have like what we know best is supervised learning, and so in supervised learning we have the data and also we have the labels for that, and using that we will supervise the network. And in self-supervised learning, what will happen is the input itself will like directly be the label, or some form of the input will be the label, and using that we will supervise the network. So we can think of self-supervised learning as something like this also, like self learning. So one of the pioneers in this field, like Professor Anlekun, calls self-supervised learning the dark matter of intelligence. So, and there's a nice article which he has written, and you can read that also. And when it comes to self-supervised learning, there are two main branches. One is contrastive learning, and we saw a couple of papers under this branch, CLR and VCREC. So the main idea, what happens is like we have, let's say, anchor image, and we create a positive and a negative pair from a single anchor image, and to create the positive pair we can like do a label preserving transformation, and to get the negative one we can do a non-label preserving transformation, or it can be any other image in the batch, and then we send it through our model and get embeddings. And what we want to do is, when we map it to the embedding space, we want to make the anchor and the positive close together as possible, and the anchor and the negative ones as far away as possible. So these are like making it closer, we call it the invariance part, and making things far apart, we call it variance. So by doing that, we will be learning the embedding space. So the basic idea here is we will use similarity and dissimilarity between things to understand the embedding space. So even as humans, what we do is like for an example, we have seen multiple versions of mobile phones, and when we see a new mobile phone, we are able to map based on what we have seen in the past. We are able to say, okay, this is also a mobile phone. So then the other branch is pretext task-based learning, and things like colorizing, inpainting, and RotNet can be thought of it. So the basic idea here is we are giving the model some pretext task. In order to do that pretext task successfully, it needs to learn the features in the image. So for an example, let's take this. So we are breaking the image into patches and then shuffling it. And the task of the model is we are giving these shuffled patches, and it needs to unshuffle them in the correct order. So in order to like create this correct order, it needs to learn the features in the image. So that's the basic idea. So in any of these cases, it's the idea. And for like the specific task, a task specific decoder will be there in all of these things. We need an autoencoder setup, and the decoder will be a task specific decoder. And then, so you can read this extremely good article on self-supervised learning, which compares contrastive and pretext task methods. And then why we need pretext task methods? Like we saw contrastive methods like CLR, VCREC, they work well, but why do we need pretext task methods then? So there are some limitations when we come to contrastive learning. One is, we saw in previous presentations as well, it depends strongly on data augmentations, and there can be certain use cases where doing data augmentations might not be possible. And also there's a research done like the performance on out of distribution data in contrastive based methods is not that good, and I will attach that paper also. And then also one thing is like in VCREC, I think we saw like we need like large batch sizes. Like they are calculating the variance loss using the batch size, like the other image in the batch. So therefore we will need large batch sizes to be successful, and also sensitivity to hyperparameters. So like there is a variance and invariance loss, we need to balance that. And also in something like VCREG, there's a covariance loss as well. So we need to balance these hyperparameters, and that could be a tedious task. And also these suffer from mode collapse. That means like for every input image, it learns to give out the same representation. And also like these contrastive based methods have been proven on ImageNet like datasets. That means like we know ImageNet has some kind of biases, and like one problem is like a center bias. Like that means the photographers have always like tried to bring the object to the center of the image. But when it comes to like datasets like, let's say, texture based datasets, like both me and Avishka have experienced that like in our internship. When we come to like texture based images, these methods have not performed extremely well. So that's why we need pre-text task based methods, and I have extracted this table also from the previous article. So as we saw, pre-text task based methods pursue a totally different direction, and also they are mainly based on autoencoders. But now when we look at the results, now these are like contrastive based methods and these are pre-text task based methods, and you can see the accuracy is much lower when we come to like pre-text task based methods. But one thing to notice is the backbone used is a CNN based backbone. So that may be the reason why pre-text task based methods up to now has lagged behind. So but now we know that we have the vision transform as well, so that brings different possibilities in. So you can read this article for that out of distribution case, not the article, it's a paper. So then I have just added this slide for the completeness. So what is manifold learning? So like when we come to data such as images and text, these are high dimensional, but we know the underlying structure in them is a low dimensional thing. So understanding that underlying structure or the manifold is known as manifold learning. So you can see that in the image as well. And when we come to manifolds, they have different shapes like this. So you can read more if you are interested in that. So now we will come into autoencoders. So understanding autoencoders is very important to understanding this paper. So when we come to autoencoders, we know that there is an encoder and a decoder like this, and I will only talk about reconstruction based autoencoders because this paper is based on reconstruction. So what we will do is we will give an input image and reduce it down to a latent representation, and using this latent representation we will try to reconstruct the image. The thing is, in order to reconstruct the image again, this latent representation should have a good understanding of the input image. And then we can say like, to do that reconstruction, it needs to like learn the data manifold kind of things, we can say. And also like when we come to the design of the autoencoder, we have to be a little bit careful. Now see here, like this is the input and this is the encoder part, and this is the latent representation, and this can be thought of as the decoder. So we are giving xi as the input and h is the latent representation, and this is the reconstruction of this. And think of a situation like this where the encoder and the decoder is symmetrical, and let's think the latent representation is larger than the input's dimensions. So in that case, the model can simply learn identity function, right? So therefore we need to be careful in designing these models. So one thing we can do is we can make the encoder and the decoder asymmetrical, and also we can make the latent representation a lower dimensional thing than the input. And another thing is like now see, like by making the decoder, like let's say if we make this smaller, in order to reconstruct back the image using this latent representation using a smaller model than the encoder, it will force the latent representation to be extremely rich, right? It needs to be extremely good, and it needs to contain all the required features only in order to reconstruct it back using a smaller decoder. And also another thing is, now let's say if this is too small, what happens there is, like now we know the decoder is specialized in reconstructing images. But if this is too small, what happens is like it will take some of the encoders layers, it will like specialize some of the encoders layers also on reconstructing the image. So that can also be a problem. And when we come to autoencoders, there are different variants like denoising autoencoders, variational autoencoders and things. So you can read more about these types also. And then autoencoding in NLP has been extremely successful. The main reason is the transform architecture, and we have seen this, and BERT showed us how to pre-train this using an autoencoder setup. So what BERT basically does is it has a like input passage or input text. We mask out a certain part and tell the autoencoder based model to predict the mask token. So in this case, we have a transform encoder, and the decoder is a simple linear layer. So the linear layer's output dimension will be the size of the vocabulary, right? That's what we know. But when it comes to vision, like up until like let's say 2020 or 2021, up until this paper came, in vision tasks, this autoencoder kind of a setup has not been extremely successful as in language domain. So the main reason for this is the difference in language domain and vision domain. So if we like think of it, the first difference is the kind of foundation models. So if we go back to like 2022, 2021, the foundation model for vision was CNNs, right? But now we know that VITs have come, but when we come to CNNs, like what we saw in BERT, like adding positional embeddings, like masking, those kind of things cannot be done in CNNs, right? It doesn't facilitate those. And then the difference in information density. Now, when it comes to language, if we saw in BERT, it's only masking on 15%, right? Now, let's think of a situation where we mask out a single word in a sentence, and in order to predict that particular mask token, the model needs to have a good language understanding and also good understanding of the context, right? But when we come to like images, now let's say here I have masked like 25%, but still like you can see, in order to like complete this image or reconstruct this back, we can do a simple like interpolation, right? We can see like here the ear is there and here this part is there, so this part I can simply predict by like interpolation, right? Or just by looking at neighboring patches and interpolating, we can reconstruct it. The reason for that is the difference in the information density. So in vision cases, we will have to obviously like mask more out than language. So like in this paper they have shown like masking percentages of like 75% will work. Like in this case, like for this image, like you can see, the model will have to have a strong understanding of the image in order to reconstruct this, right? It's not going to be easy to like do a interpolation. And then the role of the decoder. So in BERT we saw the decoder is a simple linear layer, but in vision cases the decoder should be specialized in reconstruction. So we simply can't have a linear layer like this, so we will need to have some model like a VIT or a CNN. So we saw the transform architecture in language and the BERT thing. So with VIT's introduction, what BERT does in language domain, the MAE does a similar thing in the vision domain. We can think of it like that. So what MAE does is they propose masking out random patches in an image and try to reconstruct them in pixel space. And also they are proposing asymmetric encoder-decoder design. We will see why that works. And also what they have achieved is they have achieved reduced overall pre-training time, and we will see how they are doing this. And also they are able to learn high capacity data hungry models which generalize well on downstream tasks. So that's also important. So the overview of what they are doing is they are taking in input image, masking out a certain portion, and then the unmasked tokens they will feed to the encoder, and then finally do a reconstruction of the image. So that's a high level overview, and we will go into details of each and every part. So first, looking at this masking step. So we have an input image like this, and what we do is we break it into patches. So we have seen this patching thing in many of the models. So here, as the backbone, they are using a VIT based model. So according to the variant of the VIT which they are using, this patch size will vary. They have mainly used VIT large 16 by 16 patching model. So in this case, we can think this is a 16 by 16 pixel patch, and then what they will do is they will randomly shuffle these patches, and then according to the masking ratio they are choosing, they will like select the like last part of the like mask list and the token list, and they will simply mask it out. So the thing is, like, let's say in the paper you saw, like they are choosing a masking ratio of like 75%. That means in the list of these patches they will simply mask out the last 75% of the patches. And then, like, if we reshuffle and see this is the original thing, and this is when we mask out. So you can see, like, by simple interpolation the model cannot like predict these patches, right? And then what we do is we have these unmasked patches, and then we take these unmasked patches, and you can see the order is not in a like it's not in a correct order, right? But the order does not matter in case of transforms, right? Like, so each patch, now what we will do is we will linearly project it into an embedding, and also we will add the positional embedding. So because we are adding the positional embedding, this shuffling case is not a problem, right? And then what we will do is we will feed it into an encoder. Now this case here is, now for the encoder they are using a VIT based model, and since now you can see we are only feeding the unmasked patches, we are not like feeding the masked patches. In BERT we saw we are also feeding the masked tokens, but here we are only feeding the unmasked tokens. So by doing that, what they are telling is, now let's say we have a certain number of parameters to be used in this model. If we use all, like if we use the masked tokens as well, we will have to like make this encoder wider, right? So for a given number of parameters, if we have to make this wider, the depth will have to be lower. But by only sending the unmasked tokens, we can make the model like the width we can reduce, and we can make the model more wider, right? Not wider, more in depth. And then the output of the encoder. So when we send it through the encoder, each of these embeddings now will have some contextual meaning, and also like for each of these patches it will like have an understanding what is around this, right? So that's what basically the encoder should do. And then what we do is we have the encoder output. We know this is shuffled. What we will do is we will unshuffle this and also insert the mask tokens. So for the mask tokens, they have used a special vector which is learnable, and also then we are feeding it to the decoder. For the decoder, what they have said is they are using a VIT based decoder, but they are making it shallower. We spoke in that like autoencoder setup, by making the decoder like less in depth or shallower, we are like making these representations more richer, right? So that's why they are making the decoder more shallower. And then the decoder will give out embedding, so we can think of these as like pixel level prediction. So we will see what that is. So this is what is given out in the decoder. So what this will have is, for each and every pixel, this will have the pixel level prediction. So like let's say if we have a patch like this, so this will have for like if this is a 16 by 16 patch, this will have the length of this will be 16 by 16, that means like 196. And if we like simply reshape this, we can get this. And then like this is how the reconstructions look like. Just by looking at this, I think you will be having many questions like regarding the reconstruction quality and all. So we will have a discussion on that now. So the loss function which they have used here is like per pixel. They have first tried doing per pixel MSE, and also they are only calculating the loss for masked patches. Okay, so like the unmasked patches the model is already seeing, so they are not calculating loss for that. So they have first tried comparing at a pixel level, and then they have also shown in the paper by considering each patch, if we like calculate the mean and the standard deviation of the pixels within the patch and then normalize the patch and then calculate the MSE, that performs better. And then like looking at the problems here, like you can see there is something like these patches, it looks like the reconstruction quality is lower. Why that happens is we are only calculating the loss for the mask patches. So if we closely look, these are these unmasked patches. These are coming from these unmasked patches. Because we are not calculating losses for these unmasked patches, the reconstruction quality of that is low. Now you can think like in the decoder, when it sees a mask token, it will try to reconstruct it at a good quality. But since we are not calculating loss for the unmasked patches, the decoder will not take much effort in like reconstructing them. And then like another thing is this reconstruction quality. When it comes to the like master autoencoder, the target is not doing a very good reconstruction. We have separate models to do that, but when it comes to this, the basic task is to understand the image. So now think of this. Now here in this image, the dog's ear is up, but in the reconstruction, it's not up. By looking at this, there is no clue that the ear, what is the angle of the ear. So when it comes to vision, the ear can be up, it can be down, and it can be anything in between. So there are numerous possibilities of that. So it's unfair to tell the model to exactly reconstruct this, right? This doesn't like reconstructing this exactly doesn't give any like clue of the kind of understanding of the image the model has, right? So that's not required. And also like think of this, like when it comes to language, if we mask out a single word, the mask token will be like, let's say, one of million words. But when it comes to language, when it comes to vision, if we think of a pixel level reconstruction, one pixel can be one of 256 into 256 into 256 values. So think of the number of combinations there, but that's also not that big. But in vision, a single pixel means nothing, right? We need to see a neighborhood of pixels. So now think of a neighborhood of pixels and think of the number of combinations of things which can happen. So due to that reason also, like doing a extremely good reconstruction we cannot expect, right, in vision. And also now when it comes to this reconstruction quality, they have shown like, now we saw that the reconstruction quality for unmasked patches is lower, so they have said in the paper you can simply like replace the unmasked token here and get this kind of a output. So they have mentioned that but they are not doing that. And if we think like even here after replacing these low quality patches, still the reconstruction quality, it looks blurry. But then now this thing they have not mentioned in the paper. They have, in their GitHub repo, they have given a Colab notebook. In that they have used this extra GAN loss. So by using this GAN loss, now you can see when we use that, now the reconstruction quality is much better, right? But again, the reconstruction quality is not what we are aiming for here. What we are aiming for is like getting a good understanding of the image. And then as I said earlier also, like since we are not calculating losses for these unmasked patches, the reconstruction quality there is lower. And then in a nutshell what happens is we take an image, break it into patches and then shuffle them, mask a certain percentage, only feed the unmasked tokens into the encoder, and then we get the encoder output. Into the encoder output we unshuffle them and insert the mask tokens and then feed it to the decoder and get a pixel level prediction for each patch. So what for the experiments they have done, they have mainly like pre-trained it initially and then like done an end-to-end fine-tuning and also tested it on linear probing, and they have shown what those things mean if you don't know. So in experiments they have first tested with the masking ratio. So we saw like with lower masking ratios it's not going to be helpful in vision. So they have tested out with the masking ratio first, and they have shown a masking ratio around 75% performs well for linear probing and fine tuning. So that's why they have chosen a masking ratio of like 75% as the best thing. And you can see the results here. Like now see, if we go for a masking ratio of like 95%, see, now this is what proves that this concept works extremely well. See, by looking at this part only, it's completely impossible to reconstruct something like this, right? Like it's out of the question, because by looking at this, even a human can't do that. But now see, by using these few patches which relate to this reconstruction, it is able to reconstruct the mushroom. So that means this has a extremely good understanding by looking at this patch only. Like it can understand the features within this patch and say, okay, this patch belongs to some kind of mushroom. See the kind of understanding it has gained using this. And then also now when we come to a masking ratio of 75%, now we are the model will see something more, and then it can reconstruct a much better thing. And also I should tell the values you are seeing here is the MageNet 1K validation accuracy. And then they have tested on this decoder design. So as I said, we can make the decoder shallow, right? So if we they have tested with different number of blocks in the decoder, and for end-to-end fine-tuning, see now what we will do is we will train this whole pre-train this whole model, and then we will remove this decoder, right? But if this is shallower, I said some of the encoders layers will also specialize in reconstructing. And if you are doing end-to-end fine-tuning, then again we will fine-tune these weights. So in that case, the accuracy you can see it's not a problem. But when it comes to linear probing, we will completely freeze this, right? We will only add one more layer. But if the decoder in the pre-training is shallower, as I said earlier also, some of these layers will now specialize in reconstructing. So that's why in linear probing, when the number of blocks is lower, the accuracy is lower. So, and then the reconstruction target, I think I mentioned this earlier also, they have tried with pixel level reconstruction and also pixel level reconstruction after normalizing within the patch. So by doing the normalization, it has performed better. And the mask tokens, so I said we are only inserting the unmasked tokens into the encoder. By doing that, the number of flops will reduce, and also the accuracy has also been better, much better. And also the speed up in training is also much higher when we only insert the unmasked tokens. So then we saw when it comes to contrastive learning, augmentations is a problem. So now they have shown for the MAE, augmentations doesn't matter. They have just done cropping and random resizing, and that's performing best. So things like color jitter, it has not been performing up to this level. So this shows augmentations doesn't matter in this case. And then the sampling strategies, so we can choose to randomly sample or block masking, and then also grid masking. So they have shown by randomly masking that performs better for both fine tuning and linear probing. And I can tell you if we do something like this, still that interpolation case can be done, right? So to make the task more challenging to the model, this will do the job, right? And then now this is where that scalable models in their title comes. They have initially pre-trained the model for 800 epochs, and then see for after fine tuning and for linear probing for 1600 epochs, you can see still the training or the fine tuning has not saturated, right? So that's why the more data it sees, the accuracy can improve without saturating to some value. And then these are the qualitative results. You can see just look at this, after masking it doesn't have an idea that this has horns, right? So it's completely unfair to expect the reconstruction to also have horns. there can be possibilities, right? Like there can be like these cows or whatever without horns also, right? So this only shows the understanding of the image, but it's not going into the reconstruction thing. And then they have also compared with previous state-of-the-art contrastive based methods, and they have shown the results are much better. And also now this is also another interesting result. So here see, they are training the VIT in this line. We will only consider these two lines because that's what's important. So this line, initially they have supervisedly pre-trained on this very large data set. I think this has around 300 million data points. And the MAE, they are initially self-supervisedly pre-training on ImageNet 1K. And then like after that, if they add an extra layer and then test it on ImageNet 1K validation accuracy, you can see with seeing much lesser data, this is performing very close to supervisedly learned VIT with much more data. So this shows the masked autoencoder needs to see much less data and it can perform as good as a supervised method. So that reconfirms that the MAE has, like in the MAE, the encoder will be having a much better understanding of the image. And then they have also shown like for downstream tasks like object detection and segmentation and all, it's also performing well. Yeah. So, and then like we saw that this paper is from Facebook, and in their future work which came after that also they have used this concept. So one thing is IJPA. So in IJPA, if I tell in a like high level, like we saw in MAE they are calculating losses at pixel level, right? But in IJPA what they are doing is they are calculating losses in the latent space. So that's the difference. And another thing is this VJPA thing. So I think there's a video based version of MAE, and I think this is the extension of that VJPA. This came out this year, I think 1 or 2 months old. So here also you can see they are using that masking concept. Yeah, so that's it. And yeah, are there any questions?
A small question. So when we are training, we are only inputting the unmasked tokens, but in the inference we need to do the whole image.
No. Only we are masking and only inputting the unmasked.
In the inferencing also we are only using the part of the image.
Yeah.
Won't that be some sort of a restriction to the module?
No, but now what they are showing is this has a very good understanding. By seeing only part, it can give out a good representation. So as I said, now here in the encoder, after we feed here, the encoder's output, each of these embeddings, now let's say this is the 19th patch and let's say it's somewhere here. This patch will, although the patches around it has been masked, what the embedding for this patch will say is how the surrounding patches will look like and the data related to that, and it will also represent in what kind of a context this is. So that's what it's giving. So that's why we do not need all the patches. So in a way we can think when we come to images, now let's say if this part is like this, we can say the remaining part is also going to be in a similar way. So that we can say a redundancy, right? So by looking at one patch only we can derive this. So that's why we are only using some parts. So in that way we can get the same understanding or even a better understanding of the image. And that also reduces the amount of computations and the time for inference.
Another thing is why doesn't the shuffling matter?
Yeah, so since we are giving the positional embeddings, we know in transformers the order doesn't matter, right? Since that information regarding the order is in this positional embedding.
So these are not learned embeddings.
Okay. the positional embedding. I think it's learned, right? We can make it learnable. I think in the swing transformer paper also we had that absolute embeddings and also that learnable. I can't remember the name exactly. So it can be learnable also. We can tend to make it like not learnable, and also there are learnable versions. I can't remember the exact name. They had a different thing in the swing transformer.
The learnable ones learn the position since we consistently like each of the tokens will have the same position right from the same image, and then the learnable one learns that position. Right.
I need to understand what it says.
It's like we break the image into patches and
Yeah.
we feed them to the transformer, and we consistently feed them to the same positions, and so that's how the learnable one learns that this is from this position. That's how I have understood.
Alright.
I think they're the same position.
So for each position we add a different vector, which is the positional code.
The left.
Yeah. And what it learns is the position of the image. Yeah. We are looking to it.
Yes. Instead of a sinusoid, it will include a learned function.
Yeah.
So samples from a vector samples from a learned function. I think that's what it does. I think the actual position and the positional encoding mechanism are sort of independent. You give the position to the positional encoding, it will give an encoding. They don't have to exactly match to the position for sure. Right?
I think I will
Yeah.
look into maybe.
The positional encoding scheme doesn't have to depend on the exact locations of those patches, right? For sure.
But the positional encoding, they kind of capture the new to the positional encodings of mobile patches tend to have a higher signal. That's what we saw in the VID group.
When you learn the positional encoding, do they depend on the contents of the patches or only the relative locations of the patches?
It should be the location.
Relative location only.
So it should be something like just a lookup table.
Something like that. I used to do not know too much. That's what I feel.
This encoder thing, output should be really good at image compression.
What do you mean by
I mean, because only using few of the, only like using 25% of the image, it knows what image looks like.
yeah.
So it should be usable in image compression, because using only less data, we know what the image looks like.
But here these patches have the understanding, but in compression what we mean is like it should have everything. Right?
Yeah.
But through like the decoder and all, maybe we can like reconstruct a like
Yeah, no, I mean not exactly. It might be usable in some
Yeah, yeah.
cases.
Yeah, so that was shown also by using that gamblers. So haven't they done any experiments using that
No,
gamblers?
no, no. In the paper they have not even mentioned that, but in their GitHub repo they have used that.
So maybe they tried it after.
But as I said, like their goal is not that.
Yeah, but my argument is that by doing that, the embedding might be more richer.
No, like in that way we are giving another task, right? Like
Yeah. So in the previous presentation by Johan, so they are so by using the other head, it performed by using the same structure of the clip, that clip's encoder and decoder learned well, but using another.
But now like
different decoder.
what came after that is iJava. So in iJava they are completely removing the image
Image
like
space.
pixel level thing and going for like in the latent space.
Yeah.
So doesn't that like
No,
Tell
the
the
question
other.
is whether generation is required or not, right?
Then your target is only to use the encoder.
Yeah, so my argument is by using a generator, the encoder will, the supervision signal that the encoder is receiving will be more
much
meaningful.
That's also true.
Instead of using a pixel based loss, adversarial supervision signal might be more meaningful. So that won't be possible with this iJBars. So
Yeah. Shall I quickly move to the middle?
It seems to me that we are not doing the third one, who's doing the third one. Maybe we have a staff meeting at 10:50. How shall we do that?
So here what I have done is like I try to do a comparison between the MAE and the VIT. So basically like what I did was like I took the official code from the GitHub repo, and in this, like you can see in the forward for the like for a downstream task we will only be using the encoder like for something like classification. So here, as in the VIT also, they are like appending an extra CLS token. So this CLS token will be used for things like classification. So what I did was I took from this. So I have created a new model. So what I am doing is from the encoder's output I am taking the x1, that's why this is 0, and only taking for each and everything in the batch I am only taking the CLS token. That's why I have put 0 here. So after doing that I have just put this. So these are the results. So I have just fine-tuned end-to-end on the Oxford PET dataset for like 10 epochs. So my like end goal was like the MAE should have better accuracy than the VIT, but the results does not show that. Like for the MAE on like it's the results are on par with what they have given in the paper. Like in the paper they have shown for end-to-end fine-tuning accuracies in the range of 80 is achievable. So here I was able to achieve like 87%, but the VIT's performance was better. The only reason I have is like the VIT's pre-trained weights I got from PyTorch's official version. So maybe the pre-training recipe there is a little bit different than what MAE has done in the original version. So that's the only thing I can say why these numbers are lesser. Yeah, but still these numbers are on par with what they have said in the paper. also one thing like what I noticed is the inference time for the MAE is much lesser. Like it was like half less. Like if I can remember, like the VIT took like 3 minutes for one epoch, and the MAE takes like 1.5 minutes, something like that. The reason is we are only feeding the masked tokens, unmasked tokens there.
Any other questions or comments? Shall we conclude? We thank this segment.